Hey, what's up you guys? You are watching the Kaggle Code Review Show and my name is Valerian Garbzov. Today I want to discuss with you the base principle of the computer vision with TensorFlow. Let's do it. And our talk would be based on the computer vision using TensorFlow by Umar Khan article. Thank you, Umar Khan. Deep learning is a field that is related to machine learning. It uses artificial neural networks to train a single task model to come up with solutions for a problem. The idea of computers being able to see and detect features of an object and then classify it as a certain item or face is known as computer vision. One example of how deep learning is transforming computer vision is facial recognition. The face comes into neural network in a form of images, pixels, and video, and through a series of layers it can train our model to output a certain face. Security system use this output to compare it to the database and can check all the information about this person if necessary. So computer vision is a very useful tool in practice. What is a neural network? So far we have been mentioning neural networks, but what exactly is artificial neural network? The idea of ANNs was based on the neurological system in our brain. The way our brain uses a series of interconnected neurons to create a neural network in our brain to do all sorts of things was the motivation for artificial neural networks. In deep learning, the simplest neural network compromises of a single neuron. Neural network can be split up into three layers. We have the input layer, hidden layer, and the output layer. The hidden layers are all the layers that are in between the input and output layers, in which the function applies weights to the inputs and directs them through an activation function at the output. In short, the hidden layers perform nonlinear transformation of the inputs entered into the network, deep AI. The output can consist of one or multiple neurons by mimicking how the brain operates through a series of algorithms. Underlying relationships between the data are found to make a precise estimate of our output. So let's start with setting up a neural network in Python. There are a few general steps when creating a neural network which should be the basis for any problem. These steps are fundamental to understanding how neural networks work and the different problems at hand which require tweaking of the neural network. So first of all, we need to identify the problem. What we want to get out of this article or code is to be able to feed any picture to our model. And through neural networks, it should classify what type of them it is. So as usual, we need to import necessary libraries. We would import TensorFlow as TF, NumPy for linear algebra, and TensorFlow. From TensorFlow, we would import Keras as a backend. TensorFlow is a free open source platform for creating algorithms in machine learning. TensorFlow really aids in the building of neural networks to solve complex tasks efficiently. NumPy is a library which includes concepts from linear algebra, as I told you, such as arrays and matrices, which will make sense later. Keras is a great API provided by TensorFlow and is one of the leading high-level neural networks APIs. So we need Keras for the high-level neural networks performance. It is written in Python and supports multiple backend neural network computation engines. So to identify, we identify the problem, and now we need to acquire the data. The data was provided in the MNIST dataset, which can be accessed by the Keras API in TensorFlow. It's a dataset from Google for practitioners and neural networks developers to use in different situations. Fashion MNIST is a dataset of Zalando's article images consisting of a training set of 60,000 examples and a test set of 10,000 examples. Each example is a 28 to 28 grayscale image associated with a label from 10 classes. Zalando intends Fashion MNIST to serve as a direct drop-in replacement for the original MNIST dataset for benchmarking machine learning algorithms. It shares the same image size and structure of training and testing splits. Each image in our data is 28 pixels in height and 28 pixels in width, for a total 784 pixels in total. Each pixel has a single pixel value associated with it, indicating the lightness or darkness of that pixel, with a high number meaning darker. This pixel value is an integer between 0 and 225. The training and test dataset have 785 columns. The first column consists of the class labels and represents the article of clothing. The rest of the columns contain the pixel values of the associated image. Importing our NumPy library would help us tremendously while working with the 28 to 28 arrays. And on our input images we got labels, and it's t-shirt, trouser, pullover, dress, and many other from 0 to 9. The fashion amnesty data is available directly in Keras datasets, so you remember that the Keras is a high backend API for TensorFlow, and you load it like in one line of code. Amnest equals tf Keras datasets fashion amnest. The next thing we'll want to do is split our data into training and test datasets, so we can train our model with given labels. Here it is. An interesting thing when working with images and data is visualizing it. So we'll import the matplotlib, which can help us plot our data into images that are visually appealing. For example, our first object, which is at index 0, is a boot. You can see how we use matplotlib and print train labels and train images. We can see that there are 28 to 28, and depending on the item, every pixel has its own value from 0 to 255. Then we would create our model for computer vision classification task. So our model would be sequential, Keras sequential, and we would flatten our input and use the dense layer with 128 neurons and a ReLU activation function. And at the end we would use softmax with 10 classes, a dense layer. So we define our model with a few keywords: sequential, flatten, dense, activation, ReLU, softmax. You can see it in the article. The next step is compiling our model. The next thing that is done is actually building our model. We do this by compiling our model, and there are two important parameters we need to have filled out: optimizer and the loss function. The loss function measures how much error we made or the amount of discrepancy between the actual value and what the model gave us. Then using the error value from the loss function, the optimizer function creates a better guess on the next try. So that is about the optimizer. And the metrics parameter will basically tell us our accuracy of our estimate on each guess. So we fill these parameters in the model compile. So the optimizer would be Adam optimizer. The loss function would be a sparse categorical cross entropy, and the metrics would be accuracy. Then and we need to fit our model with train images, train labels and we will do it on 5 epochs. Now we've created our model, but how will we give it the data to train on? We do this by fitting our model on our training images and training labels. On each epoch, TensorFlow would tell us the loss and the accuracy, and we see that on each epoch the loss and accuracy, the loss decreased and the accuracy increased. So our model is not overfitting. From the figure above, we can see as we have more tests, epochs, the loss of our model decreases while the accuracy of our model increases ever so slightly. And after we compile the model, fitted it, we can test it out on our test images and test labels. We would do it with the evaluate, and when we train our model, we want it to work on data that doesn't give it to the final answer, and that is called our test data. It returns a list with the loss of our model and the accuracy. In our case, our model has an accuracy of 82, while the loss is 0.56. Now that we've created our model, trained our model on the training data, evaluated our model, and seen the overall accuracy, we can now feed it images and test to see if our model predicts the right classification of our item. So we can predict the label on our test images by model predict test images and print the correct the predicted index. It's in TensorFlow, it's like one line of code. And note that all these are probabilities, is scientific numbers, and we see that the probability that is closest to 1 is on index 9. We can find out the label of this object by print test labels. So that's how it works. We can you can test it by your own. I'll give you the link on the Google Colab. So that's all about the computer vision in 10 minutes. And I would give you the conclusions. In conclusion, to end this project, we were given images from the MNIST dataset provided by the Keras library. We created a neural network by splitting up the 2D array into one-dimensional array and fed that into our input layer. After building our model and training, we evaluated on our test data and found that the model was only 82% accurate. This showed that there is much room for improvement, and we can increase the EBEX, or we can have a different optimizer. We can, as well as the last function, we can also increase the number of neurons, or we can change the model to CNNs, convolutional neural networks. And all of these are great ways to increase the accuracy of the model, but we have to take in that this is only on the training data. The more we increase the accuracy on the training data may result in overfitting. That what I was talking about little earlier. So there is a vast majority of detail we can look at to further enhance our model and understanding of neural networks. So that's the starting point for you guys. I would show you the Google Colab too. And here is the Google Colab that you can use by your own and to calculate all the steps by your own hands. So I use Google Colab for you to share with you all this code. So practice, guys, practice.
Guys, I really need your feedback, so push the like button, subscribe, and give me a comment. What can I do for you next?